Alrighty guys, so tonight we're going to be talking about different constants. And so far, we've talked about the equilibrium constant, or KEQ. And if you remember, we discussed that the KEQ is the ratio of the concentrations of products to reactants at equilibrium. And so we gave that generic expression of AA plus BB going to DD plus EE, and that KEQ is equal to the concentration of the products raised to their coefficients over the concentration of the reactants raised to their coefficients multiplied together. And we said that it was cool because this does not include solids or liquids, and something that I haven't mentioned, but something that's important, is that the only factor that actually changes the KEQ value of a reaction is temperature. So I've mentioned before that the equilibrium constant for a reaction is for that reaction no matter what you've done to the reaction, whether you've increased reactants or increased products or anything like that. And so if you change the concentration of reactants and products, it's always going to shift to try and get that same concentration ratio, or the KEQ value. The only time that that KEQ value can actually change is if you affect temperature. And we discussed the fact, and so let's talk about actually how that temperature can affect KEQ, because it's different for endothermic versus exothermic reactions. So for exothermic reactions, remember these are reactions that require heat to occur, so heat is therefore a reactant. Adding heat is like adding reactant, and therefore equilibrium shifts right, and vice versa. KEQ is also going to be affected in this. Adding heat to an endothermic reaction is going to cause the KEQ to increase, and vice versa. So here I've got an endothermic reaction where heat is a reactant. If I add heat, I'm increasing the KEQ value. So let's talk about why. If I add heat, that's going to shift my equilibrium to the right, because my stress is now that I have too much reactant, so I'm going to make more product. When I make more product, the concentrations of my products go up. KEQ is the ratio of concentration of products over reactants. The concentration of the products just increased, the concentration of the reactants just decreased. So I'm taking a bigger number and dividing it by a smaller number. That means that KEQ value is going to go up. If I remove heat, I'm going to have to shift to the left, which means that the concentration of my reactants is going to go up and the concentration of my products is going to decrease. Now I'm taking a smaller number and dividing it by a bigger number, so KEQ is going to decrease. Exothermics are the opposite. Exothermic reactions release heat. Heat is a product because of that. Adding heat is like adding product, and therefore equilibrium shifts left, and vice versa. Removing heat is like removing product, and so it shifts to the right. And the KEQ is also affected based on adding heat to an exothermic reaction causes the KEQ to decrease, and vice versa. So let's take a look at that again. Now we've got A plus B going to C plus D plus heat. So if I add heat, I'm shifting to the left, increasing my reactant concentration, decreasing my product concentration. So I'm taking a smaller number and dividing it by a bigger number, which is why KEQ decreases. And vice versa. If I remove heat, I'm going to shift to the right to try and replace the heat. Now my C and D goes up, and my A and B concentrations go down. Therefore, the KEQ increases. So there's a nice little table for you with this. Adding heat for an endothermic reaction increases the equilibrium constant. Removing heat decreases it. Adding heat causes it to shift right. Removing heat causes it to shift left. For an exothermic reaction, if we add heat, we decrease KEQ. Removing heat increases it. Adding heat to an exothermic shifts it left. Removing heat shifts it right. And so, again, we can kind of draw that. You can draw this table. This diagram is essentially a diagram of the table. So A plus B adding goes to the right, KEQ increases. Removing goes to the left, KEQ decreases. Or an exothermic, adding moves it to the left, KEQ decreases. Removing it moves it to the right, KEQ increases. Okay, so it's all kind of just a nice little summary. All right, now we want to talk about another constant, and that would be the Q sub C, or the reactant quotient. This is a constant for a reversible reaction not at equilibrium. So it's still based on the ratio of concentration of products to reactants, but now it's at any point in the reversible reaction, not just at the point of equilibrium. So if we look at an example, I've got AA plus BB going to DD plus EE, right? Same example that we've been looking at for reversible reactions. My reaction quotient is still that ratio, so it's still the concentration of the products multiplied together, raised to their coefficients, divided by the reactants multiplied together, raised to their coefficients. We still don't include solids or liquids, okay? And there still isn't a unit. The only difference here is that Q sub C can be at any point in the reaction. It can be at the beginning, the end, what have you. But it's found exactly the same way as KEQ, so there's no new information there. Now let's compare Q sub C to KEQ. If Q sub C is less than KEQ, the reaction favors reactants and shifts to the right, okay, in order to establish equilibrium. If Q sub C is greater than KEQ, the reaction favors products and is going to shift to the left to establish equilibrium. So I actually want to write this a little different, because I think it's important that you guys kind of see my little, I do a nice little kind of a cheat here. All right. Because this is the hardest part to remember, is the shifting. So I like to think of equilibrium as being the center. If Q sub C is less than equilibrium, it's to the left. That means that we favor reactants. And in order to get to equilibrium, we have to go right. If Q sub C is greater than KEQ, that means that we favor products. We're on the right-hand side. And so we have to shift left in order to in order to be at equilibrium. So that's kind of the way that I like to think about it is, and remember, is I always put KEQ in the center. If Q sub C is less than KEQ, we favor reactants. We're going to shift right to get to equilibrium. If KEQ is less than Q sub C, so Q sub C is greater, then we favor the products, and we'd have to shift left to get to equilibrium, because that's where equilibrium is, or KEQ. And of course, if Q sub C is equal to KEQ, the reaction is already at equilibrium and favors no side, and so the reaction makes no shift. And when we say favors here, we're not talking about the fact that if KEQ is greater than 1, it favors products. If KEQ is less than 1, it favors reactants. Because equilibriums can't exist at equilibrium. You'd see more reactant, you'd see more product. This favoring the side means that it's not at equilibrium yet. Hence the fact that you were a Q sub C, not a KEQ. So let's take a practice problem. Oh, I didn't realize that I forgot to animate this. But let's go ahead and look through this. So given the following reaction concentrations and KEQ, determine the value of Q sub C and which direction the reaction will shift at the current position. So my equilibrium is carbon monoxide plus water making carbon dioxide and hydrogen gas, and the KEQ is 1. My carbon dioxide concentration is 2 molar, carbon monoxide is 1 molar, hydrogen gas is 2 molar, and water is 1 molar. So the Q sub C is just going to be my concentration of my products over the concentration of my reactants. So CO2 to the 1 times H2 to the 1 over CO to the 1 times H2O to the 1. If I plug in my concentrations, I get a Q sub C of 4. That means that my Q sub C is greater than my KEQ, so Q sub C is favoring the product side, so it would have to shift left. Okay? Nothing too complicated. Now, solubility product, and my animations got all screwy. I don't know what happened here. So there's another constant we can talk about, and that would be the solubility product constant. And what this means is that different ionic compounds have different solubility constants, meaning that different amounts of them will dissolve in water. A small KSP means that you are not very soluble in water. A high KSP means you're very soluble in water. So if we think about it, that would be like XAB being dissolved in water and breaking up into YA plus ZB minus. Okay, so your aqueous ions. Just like with all of our other constants, I don't know, well, okay. Just like all of our other constants, it's going to be the concentration of your products over the concentration of your reactants. So I've got products A plus to its coefficient and B minus to its coefficient over ABX. Now the thing is this also doesn't include solids or liquids, just like any others. So since these are solubility constants, that means that the reactant is always going to be a solid, So it's always going to go away and not be included in the denominator. So you can really just think of KSP as being some cation raised to its coefficient times some anion raised to its coefficient. So an example would be silver chloride dissolving into silver plus ions and chlorine minus ions, and the KSP would be equal to the concentration of your silver ions times the concentration of the chlorine ions. Okay? So this one's kind of a really easy one because you get rid of that whole denominator issue. Now, if KSP and how that relates to Q sub C, in order to determine if a precipitate will or will not form, you can actually compare Q sub C to KSP. So if Q sub C is greater than KSP, the precipitate forms. If Q sub C is less than KSP, there's no precipitate formed. Kind of like, it's just something that you're going to have to remember. So if Q sub C is high, that means a precipitate forms. If it's low, no precipitate forms. Okay? So, given the following reaction, ion concentrations and KSP value, calculate the Q sub C for the reaction and determine if a precipitate will form. So we've got calcium carbonate dissolving into calcium 2 plus and carbonate 1 minus, with a KSP of 3.8 times 10 to the minus 9. The calcium 2 plus ion concentration is 4 times 10 to the minus 5 molar, and carbonate is 2 times 10 to the minus 3 molar. So the Q sub C is going to be equal to my calcium concentration to the first power times my carbonate concentration to the first power, which is 8.0 times 10 to the negative 8. Q sub C, because it's negative 8, is larger than KSP of negative 9, and therefore, yes, a precipitate will form. So we're going to be practicing these different constants and using them to answer some questions tomorrow. And I'll give you kind of a handy grid to look at the different effects that you've got going on, both for equilibrium shifts, KSP, Q sub C, all that jazz. So I look forward to seeing you guys tomorrow. Have a good night.